The year was 1925, and atomic theory rested on the Bohr model, where electrons occupied states in shells. Already in Bohr's original derivation, these states are essentially quantized states of angular momentum. Certain occupations of these shells were identified to be particularly stable, such as even ones and most prominently 8. This leads to the chemically inert noble gases, while one extra electron gives you, for instance, the highly reactive alkali metals. But without knowledge of spin, the phenomenological rules to occupy these shells were complicated. One way to discriminate the states is by breaking their degeneracy via the Siemens Effect. And Pauli came across a work by E.C. Stoner, who remarked that alkali metals then displayed the same number of energy states as the number of electrons required to fill the shell. Pauli realized that this could be achieved by adding an additional fourth quantum number into the picture, which would be able to just take 2 values. And with this, each state with given quantum numbers can only be occupied once. So Pauli actually achieved 2 things at the same time, namely introduced an intrinsic degree of freedom of the electron along with the exclusion principle. This additional degree of freedom was identified by Houtsmit and Uhlenbeck as the spin of the electron. We are still in 1925, so they quickly made the connection to the observation of the correspondingly quantized states by the Stern-Gerlach experiment in 1922. Well, thanks to Heisenberg and Schrödinger, the orbital part of angular momentum, and in particular its role in the hydrogen atom, was put onto firm footing in 1925 too, and so the following picture emerged. The periodic table of elements contains atoms of increasing atomic number Z, organized into columns known as groups and rows known as periods. The atomic number equals the charge of the nucleus, hence the number of protons it contains, with the remainder of it made out of neutrons. Differences in the number of neutrons give us different isotopes. The nucleus can itself have a finite spin, which is half integer when the number of nucleons is odd, and the resulting magnetic moment is what we would probe in nuclear magnetic resonance, just to make some connections to earlier material. For the main picture developed here, however, we only care about the atomic number Z and the associated electric charge. In a neutral atom, and this is what we are concerned with, this positive charge is compensated by a corresponding number of negatively charged electrons. In the first approximation, we assume that these electrons do not interact amongst each other, which again can be partially justified by screening. And we also ignore any energetic contributions from the electronic spin. With this, we can first study a single electron problem in what we call a hydrogen-like atom. The only difference is the charge of the nucleus, which changes the radial dependence and energy via Z-dependent factors multiplied to the Bohr radius and the Rydberg energy. What stays fixed is that there are 3 orbital quantum numbers, n, l, and m, and to this we then add the spin as a 4th quantum number. As before, we will denote these orbitals by symbols 1s, 2s, 2p, and so forth, so this does not include the magnetic quantum numbers and also not the spin. This means that these orbitals can be occupied a number of times, and in particular the s orbitals can be occupied twice, the p orbitals 6 times, and the d orbitals 10 times. We will identify these occupations by superscripts. Now a neutral atom contains Z such electrons, and so we occupy these hydrogen-like orbitals correspondingly, starting from the lowest available ones and adhering to the Pauli exclusion principle. Still ignoring any interactions, the energy of these occupied states only depends on the principal quantum number n, and the total energy is just the sum of these energies. This gives us the ground state, which really determines the chemical properties of these atoms. A systematic picture then arises when we go through the list of available orbitals as we successively occupy these with increasing atomic number Z. For Z equal to 1, we just have hydrogen, which in the ground state has the electronic configuration 1s1. For Z equal to 2, we have helium, the first noble gas, and there we have the electronic configuration 1s2. This is very stable and hence chemically inert, because it requires considerable energy to excite any of these electrons to the next available state, which has a different principal quantum number. Furthermore, the resulting charge distribution is spherically symmetric. We call such configurations filled shells in a nod to the original Bohr model, and all additional electrons beyond the filled shells we call valence electrons. This exhausts what we can do with the principal quantum number n equal to 1. So we move on to n equal to 2, where we have 4 orbitals arising from the angular momentum, 1 times s and 3 times p. And we can occupy these with spin up or spin down, and so we have 8 states in total. This gives us the next row or period in the table. This starts with the first alkali metal, lithium, which has the helium configuration plus an extra valence electron in the 2s orbital, and ends with neon, which is another noble gas, and again has a completely filled shell. Just before neon we have the first halogen, fluorine. We could go into more details here. For instance, the 2s orbitals are filled before the 2p orbitals, and the latter are then first filled each once by electrons of the same spin. This is because of energy corrections from the interactions that we have ignored and is captured qualitatively in what is referred to as Hund's rules. The next period follows the same pattern with the occupation of the 3s and 3p orbitals, with the elements placed below each other sharing similarities in their chemical behavior. This is really because in most of chemistry only the valence electrons beyond the noble gas configurations matter, as exciting an electron from a lower lying orbital into an available one requires a relatively large amount of energy. From this point onwards, additional energy differences play a more important role. Namely, the 4s orbitals are filled before the 3d orbitals, and similarly 5s before 4d and so forth. As we fill these d orbitals, we cover the transition metals. This is also called the d block. And the f orbitals are filled even later, giving rise to an extra block covering the lanthanides and the actinides. In these d and f blocks there are again some reconfigurations due to residual energies, such as in silver, where one electron is transferred from 5s to 4d, which occupies all the d states completely. However, with this we get to a level of detail that does not concern us here. To conclude this segment, let me therefore just mention that this of course forms the basis of chemistry and material science. For instance, besides the residual energies, we could next explore the states when we bring several atoms together. And then we find that it can be favorable for the atoms to share some valence electrons, leading to molecular bonds, or even transfer electrons more or less completely from one atom to another, which results in ionic bonds. Here and in general, ions are just charged atoms with some additional or missing electrons compared to their neutral configuration. And of course we can also excite individual atoms or molecules in various ways, not just electronically, but also say vibrationally or rotationally when we consider the relative motion of the atoms in a molecule. And finally, when we bring many atoms together, we end up with materials, for instance crystalline solids. In these solids, some electrons may then be more or less free to move through the whole system, giving us metals and semiconductors. But these are then systems with a macroscopic number of particles and with accordingly macroscopic emerging properties as captured, for instance, by thermodynamics, for which we need to adopt a broader point of view. And so to describe such and other systems from this macroscopic perspective, we move on to the second main part of this chapter, namely quantum statistical mechanics.